All right, so 6.1 and 6.7, that's the last two sections we have to do. But now we're moving away from the logarithmic equations, expressions in the exponential. Now we're going back to more of like linear equations, so at least that's good. And we're familiar with those more. But we're going to be talking about a system of linear equations in two variables. So you've had to have heard of this before in high school. You might not remember, but you definitely learned about it in high school and probably middle school. And then if you had intermediate algebra, this is probably like the fourth time you're seeing this, okay? So hopefully this will be a little bit easier than what we've been doing. But this is an example of a system of two linear equations in two variables. So when we talk about a system, I'm talking about we want to know the solution to the system is where these two lines intersect, the point where they meet at. So I have a picture of those two lines actually graphed there. Remember, we can graph lines. We've already learned how to do this by either finding 2 points that lie on the line or by using the slope-intercept form of a line. So we've learned those techniques of graphing, and hopefully we will remember that because that will be on your final for sure. And so they've graphed these two lines in this picture, and the solution to this system is that point you see where they intersect, the 2, -3. That is the ordered pair that makes both of those equations true, and it's where those two lines intersect. So the solution to a system of two linear equations and two variables is always going to be an ordered pair because it has to be a point that makes both of these equations true. And when I say it makes both of these equations true, I can plug in the 2 for the x value and the -3 for the y into both of these equations here, and it will be true. So if I plug in 2 for x to equation 1, that would be 2 minus, and then y is -3, so that's a double negative there. And that changes to 2 plus 3, which is 5. So that is true for the first equation, but it's also true for the second equation. If I plug in 2 for x into the second equation, that would give me 2 times 2 plus y, which is -3. So this would be 4 minus 3, which is 1. So that also makes the second equation true as well. And it's the only point that will make, the only ordered pair that will make both of these equations true because they only intersect once in that picture. Okay? So that's what we're looking for when we're trying to find the solution to the system of equations, the point where they intersect. And we're going to see that this can actually be an infinitely many points if they are the same line so I'm going to scroll down. Is that okay? Good? Okay. So there's 3 different cases for these systems of linear equations. The first one we just seen in this example here, where they intersect. This is a different 2 lines, but it's still that same case. If they intersect at one single point, then the solution is just one point. There's just one solution, and it has exactly one common point. So if a system has at least one solution, then it's called consistent. If it has at least one solution, it's called consistent. So this is consistent. The other case that I was trying to allude to is that if it has an infinitely many solutions, that is when they will be the same line. So that's this case over here to the right. That's why you don't see the blue line, because it's lying on top of the blue line. So they are the same line. Sometimes they'll give you a system and the two equations represent the same exact line. I'm going to show you how that is, or what to look out for that. But it's possible. And so all the points on that line would be the solution, because they're lying on top of each other. So all the points on the first line will make all the points on the second line true as well. So those two, the lines are identical, and they have an infinitely many solutions, but it's still called consistent because it had at least one solution. The one in the middle, this is an example of two parallel lines. Two parallel lines will never intersect. It's the definition of parallel lines. So they will have no solution. There will be no solution. They'll never meet. They'll never intersect. And if you solve a system and it has no solution, then you automatically know those two lines are parallel. So when it has no solution, this is called inconsistent. So that's the only case that would be inconsistent. They don't have a solution. And then as far as the independent-dependent vocabulary words here, the first two cases are called independent because they are two separate lines. They're independent of each other. They're unique. They're their own thing. They stand alone. But the last one, they're identical. They're the same line. So those are dependent, or one lies on top of the other, one depends on the other. That's kind of how I remember that. Those are dependent. So if they're different lines, they're independent. But if they end up being the same line, they're dependent. Okay, so that's just some vocabulary for us. Good? Okay. All right. So there's three different methods we can use to solve a system of equations. The first is kind of like what we've seen in the example. We can graph the two lines. We can graph both lines on an XY coordinate plane and then find the point where they intersect. I'm not going to really do that today because we should know how to graph lines by now, but I'll probably be going over that on the review day. But also it's kind of hard to do that by hand because if you graph a line by hand on your paper, then it might be hard to see where they actually intersect, because it's not like exact, unless you have graph paper. But you could do it on your calculator and find where they intersect as well. You could just, but you would have to solve them for y, and then plug in the other side of the equation for the function and find where they intersect, blah, blah, blah. But it's possible, we can do that. But we're going to focus on these two methods, these other two methods. So the first is called the substitution method. So I'm going to kind of just explain the steps of this with this example down here. This little paragraph kind of just tells us a little information about it. It gives us accurate results. And we usually use it when it's easy to solve one of the equations for another variable. If it's really easy to get one of those variables by itself, then we can use the substitution method. And we do this by substituting one of these equations for one of those variables into the other. And then we solve that for that variable, and then we plug it back in and find the point. But let me just write it out for you instead of trying to say it. Okay, so if we do the substitution method, the first step is to solve one of the equations, one of the equations for one of the variables. It doesn't matter which equation you choose, and it doesn't matter which variable you solve for. You have that choice. You can pick whatever you want. I'm going to choose to solve the first equation here for x, because it's really easy just to add y to both sides. So I'm rewriting equation 1 here, and I'm just going to add y to both sides. So that gives me x by itself, and then x would be equal to y plus 5, or 5 plus y, however you want to write it, doesn't matter. So plug that into equation 1. Step 2 is to take what you just found that x is equal to, so all of this, we just found that x is equal to y plus 5 for the first equation. Remember, our goal is to find where these two lines are equal. So if x is supposed to equal y plus 5 in the first equation, then if I want to find where they're equal, then it should also equal that for the second equation. So I'm going to plug that y plus 5 into this x into the second equation. So I'm going to write this as substitute y plus 5 for x in equation 2. So this would be 2 times y plus 5 plus y equals 1. And just notice that this gives me an equation only in terms of y now, so I can solve for y and figure out what y is equal to. So I'll distribute that 2, which will give me 2y plus 10. Bring down the plus y equals 1. And I'll draw a little arrow, solve for y now. That's what we're doing. And then 2y plus y is 3y. Bring down the plus 10. Subtract the 10 from both sides. So 3y is equal to negative 9. Divide by 3. So y is equal to negative 3. So this is the y coordinate of the point where these two lines meet. That's where they are equal. But remember, the solution is an entire ordered pair. So I have to figure out the x coordinate now. So step 3, I will take that y equals negative 3, substitute negative 3 for y into either of those equations. It doesn't matter which one. Into one of the original equations. So I'll just plug it into the first equation. So this would be x minus, and then y is negative 3, so I plug in another, there's a double negative there. So that will give me x plus 3 equals 5, and then I would subtract 3 to both sides. So x would be equal to 2. So my final answer is the point 2 comma negative 3. Just remember, x always comes first. in your ordered pair. Okay? So this is how you will always do the substitution method. You just solve one of the equations for one of the variables, doesn't matter which one. Then whatever you get for that step one, you're going to substitute it in for that variable into the other equation, then solve that equation for whatever variable is left. Then once you get the answer for one variable, you substitute it back into the original to get the answer for the other variable. It's just a lot of substituting. Okay? Good? All right, the next method is called the elimination method. This is sometimes called the addition method. By the way, you can use either one of these two methods on any of these problems and get the same answer. So, you know, it really doesn't matter which one you use. Even if Pearson tells you use the substitution method, you could use the elimination method if you wanted to, if you like it better. So it really doesn't matter which one you use. It'll always work. Okay, so the elimination method, again, like I said, is sometimes called the addition method. So this is where we add the two equations together in order to eliminate one of the variables. But this will only happen if the coefficients are opposites of each other. Like, for example, negative 3x and 3x are opposite. So if I add those two together, it'd be 0. And these are called additive inverses. So if the two systems do not have an additive inverse, sometimes we might need to use multiplication to multiply a system by a number, or multiply one of the equations by a number to create additive inverses. So we're allowed to do that. We can multiply an entire equation in a system by a constant. But let's see how this works for number 2. So number 2, I already have some additive inverses here because the y, positive y, and negative y, those are additive inverses. They're opposites of each other. If I added those two together, they would cancel, right? So I already have additive inverses, so I don't have to worry about that. So step 1 here would be to add the two equations together. And I'm going to talk about what that means. So first of all, before you add two equations in a system together, you need to have all the variables lined up and all the constants lined up. So they already are in this case. I have all my x's on the left and all my y's on the left of the equals, and then the constants on the right. So if one is all crazy and like only has an x on one side, you need to move everything to the same side. They need to be lined up. These x's are lined up, these y's are lined up, my equals are lined up, and my constants are lined up. Okay, and when I add these two together, I'm just going to add down vertically my like terms. So 2x plus x is 3x. Y plus a negative y is 0, so that cancels. Bring down my equal sign. 2 plus 7 is 9. And then step 2, I will solve the remaining equation for the variable. So now I just have 3x equals 9. So I just divide both sides by 3, and that will give me x is equal to 3. And then step 3 will be similar to what we just did in the other technique. I have a value for x now. I can plug it back in to one of the originals and get the value for y. So substitute 3 for x into one of the original equations. So I'll just pick equation 1, but you can pick whatever you want, whatever you think's easier. So this would be 2 times 3 plus y, bless you, equals 2. 2 times 3 is 6. Subtract the 6 over. So y is equal to -4. So my final answer is the ordered pair. The x has to come first, so that's 3, -4. So that's all you'll see on that handout, but I am going to show you 2 more examples real quick while I print these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so by the way, both of these problems we just did, they had one single answer. One single point. So they were both consistent because they had at least one solution. They were both independent because if they only had one single solution, then that would be 2 lines just intersecting. So they're 2 separate lines. And yeah, that's all I wanted to say about that. All right. So I wanted to show you 2 examples where, one where you would have no solution and one where you would have infinitely many solutions. So this example is going to be the system x plus y equals 3 and x plus y equals 5. So for this system, I can use either method. You can always use either method. So anyways, let's use the substitution method. Just to refresh. So step 1, I will solve one of these for one of these variables. So I'm just going to solve equation 1 for x. So that would give me x is equal to 3 minus y, because I'd have to subtract y over. And that would give me 3 minus y. Step 2, I will now plug this in. If this is what x is supposed to equal to for the first equation, then I'll plug that in for this x in the second equation. So that will give me 3 minus y plus y equals 5. And what happens? The negative y and the positive y cancels out, and that leaves me with 3 equals 5. And this is a false statement. So remember when we learned how to solve just linear equations? If everything canceled and it was false, then it was no solution. There's no solution to that equation. So this is very similar. If everything cancels, no matter what method you use, and it's a false statement, then this is no solution, which means it's inconsistent. And if there's no solution, then they are parallel lines. And they are also still independent because they're two separate lines. But no solutions means they'll never intersect, so they are still two unique lines, so it's still independent. But this would have no solution. Okay, and then the other example, if I had x plus y equals 5, and then I had negative 2x minus 2y equals negative 10. If I had something like this, now I'm going to use the elimination method just to review that method. Okay, so in this case, if I use the elimination method, I don't have any additive inverses right off the bat. If I added x and 2x, that doesn't cancel. Y and negative 2y, that doesn't cancel. So I need to use multiplication in step 1. To create additive inverses. Or opposites coefficients. So I could multiply equation 1 just rewrite this by what? What could I multiply equation 1 by? 2, positive 2. Now if I multiply equation 1, I have to multiply everything by 2 in equation 1. So that will leave me with a positive 2x plus 2y equals a positive 10 for equation 1. And then the second equation will stay the same. Now notice that these are exactly the same equations, just one's negative. That's a huge indicator that these are going to be the same line. If one equation is a multiple of the other equation, then it's automatically the same line. So actually I could have seen that from the very beginning, because this equation is a multiple of this equation by a factor of negative 2. So anytime they're multiples of each other, they're the same line. But anyways, let's keep going and add these together. The 2x and the negative 2x will cancel. The 2y and the negative 2y will cancel. So that'll leave me 0. And then the 10 and the negative 10 will cancel and leave me 0. And this is true. 0 is equal to true, so that's a true statement. So if everything cancels and it's true, then it means that there is an infinitely many points as the solution. And more specifically though, the solution would be all the points that lie on the line x plus y equals 5. I just picked one. I could pick either one, but they're the same line. But all the points that lie on either one of those lines is the solution. So it's not that I can plug anything in and it'll be equal. It's just if it's a solution to the first one, it'll be a solution to the second one. So all the points on the first line are solutions to the system. And so this is still consistent. And they are dependent because they are the same line. So that's how you can tell if there's no solution or infinitely many solutions. It all cancels and it's true or false. All right, now we can do 6.7. I probably won't be able to finish it, but I will. Oh, let me